Good morning, guys. So finally, we are here, not in online world, but in reality, and we start our linear algebra course. Good. So I know why you are here. You are here to become a great data scientist, and certainly this poses the question, why are you here today, this morning, on this linear algebra course, which has probably nothing to do with becoming data scientists? So my first question is, why linear algebra? Or maybe that should be the second one. First question is, what is linear algebra? So what, in your opinion is linear algebra? What it is all about? So what? Matrices. Matrices. Okay, good. So matrices. What for? Equations?
No, calculation.
Calculation.
Driving some.
Okay, so this is just convenient way of organizing data. So why 20 lectures on organizing data? Just write them in a table and that's it. So what is linear algebra actually about? Optimization problems. Okay, it's again language to conveniently work with functions of many variables and performing optimizations in many dimensions. What else? That's a good suggestion as well. What else? What is linear algebra? What does it study?
Linear space.
Linear space is good. And if we develop this line of thought, I would even add transformations between linear spaces. Okay, so actually linear algebra studies linear transformations between linear structures. Why linear? Well, our world is by no means linear. Why do you care about linear?
Often can be approximated linear structures.
Yes, that's a very good suggestion. Actually, before we try to study more complex objects, more complex models, it's a good idea to understand what happens in the simplified setting when everything is supposed linear. And it is actually not only simplification, it's also a very good approximation. Look, any complex, regular, so smooth behavior in a small vicinity can be approximated by a linear one. So if you drive your car and you see your speed, it's just approximation of your speed based, so the speed based on linear approximation of your movement. So any function, if a point is not a singular point, can be approximated by a linear in a small neighborhood. If you have a function of many variables, can we perform a linear approximation as well? What is it then? It's what?
Solid plane.
Yes, it's actually tangent plane or tangent hyper space. That was me. So that explains why linear. So linearity is a very good approximation. It's the first step to understand more complex phenomena. And actually, although this course is called linear algebra, but we'll study also nonlinear things. For instance, quadratic forms are already nonlinear. They are of degree 2, and so on. Good. So that explains why linear, what is linear algebra about, but still, okay, who cares? Why is linear algebra in these programs? Oh, I personally have several arguments. First of all, when I joined this program, all cool courses were already taken up. And I could not teach, for instance, machine learning, so I'm just hopeless. So that was a trade-off. So I agreed that that there will be linear algebra. Okay, that's from my personal point of view. But then, look, there are two other reasons. The first is you have to learn linear algebra because it is in your syllabus. Well, it's a kind of not very optimistic piece of news, but a little more optimistic is that it is on your syllabus because you have to learn it. And why you have to learn it, that's yours to discover. So now what we'll do, we'll split in small teams, 5-6 persons, so say 6 here, 6 there, over there, so 4 groups, and you quickly, in 2 minutes, discuss find as many reasons why you should learn linear algebra as possible. And I'll even do the following thing. So start working. So you should be able to give very short reason, not the whole essay, but just a few very short reasons. So there are 1, 2. Okay, so your brainstorm is approaching the end. So how many did you find? 4, 6? 3? Okay, good. So let's start. So who'll start? Please start. So what was your reason? Just name one at a time. Okay? Just first.
Describe the world.
Describe the world. Good. Well, good world. Next. Your team. Your first reason.
basics for feature algorithm, machine learning.
Okay, so basics for algorithms. Next. Next one, please.
It could be great fit for brain, very interesting tasks, etc.
Okay, so brain food. Next one. So real world systems, models, yes. Good. Next one. Again, yes. Are you? You have the whole team. You have the team of 6 persons, or? Okay. So one more. Good. So once again.
It has lots of
Applications. Applications. So this is a real world model. Next one.
To be able to work with multi-dimensional spaces.
So multidimensional. Good. Next.
It is used for computer graphics.
Graphics. Computer graphics. Then, guys, wake up.
You know, we have our own model decides all the things.
Okay, good. Next. Any? Read scientific papers. You haven't chosen the easiest way to read scientific papers, but scientific papers. Anything else?
Maybe that's basic for all another courses in mathematics, like basic courses.
Well, I am of course pleased to hear that, but it's not only linear algebra. Of course, all math is a basis for everything in this world. Okay, good. So basis for math.
It could be the great time to spend.
Well, don't jump into conclusions. It's just start. So we'll see what you'll say at the end of the course. Yes.
To understand the basics of
Neural
neural networks.
networks. Yes, neural networks.
It also completely describes some complex notions, like avoids writing down a lot of.
Okay, so useful language, yes. So anything else?
To understand LaTeX, to learn LaTeX.
Well, it's LaTeX. No, that's okay. It's very non-trivial pronunciation. Good. Anything else? Optimization of algorithms. So that was your team here. Optimization of algorithms. Optimization of algorithms. So algorithms were somewhere already mentioned, but anyway, good. So these are so many reasons to learn linear algebra. But I'll continue. I'll help you to find a little bit more. So look, there are 2 lists. Well, the first is very short, the second is longer. So Google Netflix Grammarly. And 3 dots. Can you continue, and can you detect anything special about this list? That's the first list. Visual intelligence, yes, certainly good.
In Google, in PyCharm, they use eigenvector and then get eigenvalue. So
Yeah, so linear algebra is here. It's PageRank algorithm, the greatest algorithm for what? For ranking what?
Pages.
Pages. Well, actually not. There is only one page. You know, it's page. It's Larry Page.
Yeah.
PageRank is okay, but that's very, very, of course, funny in this combination. Good. Netflix. What? recommender systems, Grammarly, NLP, and so on. You see, all these things are actually linear algebra. Good. Anything special about the second list?
Algorithm.
It's an abbreviation of 3 letters.
Yes. So it's just 3-letter abbreviations. Anything else? How many you don't recognize? Okay, so barbecue is just for fun, of course. What's next? BBC, CNN. Okay, yes. Starting from the third, all these are great algorithms of linear algebra. Well, with a few exceptions, you take any 3-letter abbreviations, and there is a great linear algorithm behind it. So barbecue is out of question, of course, but maybe there is something related as well. Good. Then what do you think is special about this list? Oops. I'm quicker than this laptop. Applications of linear algebra. So I'll tell you a secret. These are topics for linear algebra projects of the last year students. So you see that there is plenty of different topics, even areas. So if we were not in this room, because now you suspect it has to be related to linear algebra, but in general, there would be difficult to even tell that there is anything common behind these titles. But actually, one common thing at least is that all of them are about real-world applications of linear algebra. Okay, and then we come naturally to the structure of this course. So what we'll be doing for the next 20 lectures. So our course is naturally split in 8 topics, and here are these topics. First 5 are basically standard linear algebra, and the last 3 will be about some numerical topics. So iterative methods of solving linear systems, for instance, and numerical optimization, which already was mentioned several times today, and say least square methods, which are applied to a great deal of problems. Good. So all the details are on CMS. Have you seen the syllabus on CMS? Was it easy to find? Good. Because sometimes my students say that there is no syllabus. Yes, there is no word syllabus, but all the topics which are in syllabus are there. Okay, so there are very, very few prerequisites for this course. The first is that you still have, this is master level course, so you still have to know how to add matrices at least. And that's basically probably all. And the same with in calculus. Well, sometimes you'll have to add fractions or take derivatives, but that's again all. And maybe another one is this one. Good. So the grading system is very simple. You work and you get 100 points. And these 100 points are split between coursework and final project. So we have 8 topics. For each you'll get 10 points. And these 10 points for first several topics, 5 of them, will include 8 points for homework and 2 points for quiz. And then, well, we'll also have occasionally quizzes during lectures without grading. And yes, final project will be a team work project. So form teams of probably two people, 2 persons in each, and choose some cool topic you would like to study, and then you'll present your results of your projects at the very last 2 lectures. Last 2 lectures will be for project presentations. So your work will include actually work, writing a report, and presenting it for all of us. And there are standard grade distributions, but I'm sure you are not interested in the last line, just in the first one of 2. Good. So that's probably, yes, a few words about code of honor, academic honor. We have very special mode of studying. I mean, we only gather here for 3 days every other week, and therefore most of the work is your own in groups or remoted groups and so on. We encourage you to work in teams, to share, to discuss, but please, if you submit your homework for grading, make sure it's your own work. What does it mean? If you discuss and solve some of all the problems together, please then split and write your solutions individually. Okay, so you have to understand the solution and then just present it in your own words. Okay, so just to be sure. Good. So let's start with the first topic, and that's a good start to start with the quiz. So go to CMS, and there is in the first part for this first course, there is quiz at the very bottom. Do you see it? Basics of linear algebra. Do you see it?
Yeah.
Why not? I do see. Is it there? So, are you logged into CMS?
Yeah, we can start.
Yes. So there is a short quiz of 10 questions for 5 minutes. Start. I didn't show what. So, are you done? Okay, I see that most of you are already done. So, do you see the results? Not yet. Good. How many times did you answer yes? 0. 3 times.
One is over, one correct.
4. 2 more. Actually, in this quiz, there is only one answer yes, which is correct. It depends because everyone has a different order. Probably Okay, so the only answer yes was for the question that if rows of a matrix are rows and columns of a matrix are linearly independent, then this matrix must be square. So that's the only question requiring answer yes. Okay, good. So this was just to wake you finally up, and then we'll start with the very simple things. So today's lectures are just to review the concepts that you all know very well, and but the reason for doing that is that maybe still I'll show you a few tips how to look at several things, how to maybe you don't know how to multiply matrices. We'll show you how to do that, because that will be very often used in our arguments. Okay, so the first, there will be five parts, and the first is just very basic things about systems of linear equations. So we understood why linear systems are important, because linear systems describe very good approximations to very many complex phenomena. So in very many situations, we are led to the task of finding unknowns, x1, x2, and so on, and of them together, which satisfy a certain set of linear relations, so linear equations of this form. And of course, we don't write it in this way. We use a shortened notation, so we will write it as ax is b. And this is not just shorthand notation, but there is actually multiplications of a and x behind. So ax is a multiplied by x, which you certainly know. So this a is coefficient matrix, b is right-hand side, x is a vector of unknowns. And although we will assume that all vectors by default are column vectors, we'll usually write it in this way. So you understand what this T stands for? Yes, it's transposition. And why do we prefer this form? Easier to write. Yes. Any other suggestions? Yes, to save the world. So this takes less space, less paper than to write it as a column. Good. Observe that this is linearity, means that actually this ax, so left-hand side in this equation, in this system, this left-hand side depends linearly on x. And linearity on x means linearity as a vector x. So this mapping, which takes x and returns ax, is a linear mapping between Rn and Rm, where, just to stress, all matrices in this course are unisize. All of them will have size m times n. So whenever I use m and n in this course, m is a number of rows, and n is a number of columns. So although the matrix has size m times n, still it acts in the other way around. So it doesn't act from Rm to Rn, but from Rn to Rm, vice versa. And yes, already here we understand that actually whenever we have matrix, this matrix is not just that array of numbers. This is an action. So every matrix is actually a transformation from one space to another space, Rn to Rm. Linearity means that if we take x and y, two vectors of unknowns, and add them and apply a, then that's the same as just adding up the separate outcomes of applying a to x and to y. So this is one part of linearity. This is additivity, and then the other part is linearity with respect to multiplying by a constant. So whenever we have a constant c, then a times applied to cx is the same as c times ax. The result of this linearity is the following structure of the solutions to a homogeneous system. So what is a homogeneous system? Homogeneous system is the system where we have to find x satisfying 0 right-hand side. And this linearity automatically implies that whenever we have two solutions, the sum is also a solution. So if ax is 0 and ay is 0, then the right-hand side here will be 0. But then it means that x plus y is also a solution. Another corollary is that if we have a solution and we multiply it by a constant, then this c times x is also a solution. Because look, if ax is 0, then we see that the right-hand side is 0, and therefore the left-hand side is also 0 as well. It means that actually the solution set to a homogeneous system, that is all x's for which ax is 0, has a special structure. It's a linear subspace. Do you know what the subspace is? Linear subspace. Yes. So whenever we have two elements in this solution set and we add them up, the result will still be a solution. So again, in this set. And if you multiply any solution by a constant, it will remain in this solution set. It means that the solution set itself has a structure of a linear space. So it is a subspace of Rn. So in other words, if we have a space so ax from Rn to Rn, m, and the solution set is just a linear subspace of Rn. So linearity means that it is, for instance, in R3, linear subspaces are just a line. It's one-dimensional subspace, or a plane, two-dimensional subspace, or the whole R3 itself. And subspace means that actually this plane passes through the origin. So the origin, this point here, 0, it belongs to this subspace L. Good. We can also understand the structure of the solution set to a non-homogeneous system. So whenever we have equation ax is b, then we can easily derive from these equalities, that from these properties, that that any solution to this system can be written as the sum of two components. We can take any fixed solution to a non-homogeneous system. So this is what we call X particular, X bar. And then any other solution is in fact just sum of these fixed solution, and any solution to the corresponding homogeneous system AX is 0. Why is it so? Well, if you just consider these two systems, assume X is a particular solution, Y is a solution to a homogeneous system, and we add these two equalities. So what we'll get? We'll get AX plus AY, but we know that it can be written as A applied to X plus Y. That's on the left-hand side. And on the right-hand side, we'll have B plus 0, that is B. So from this, we see that A applied to X plus Y is B. So adding any Y, which is in the solution set to the homogeneous equation to a particular solution, still keeps the sum in the solution set for a non-homogeneous system. And vice versa, actually, if we have two different solutions, if you have a solution X and a solution Y, so if we now have here B, and we this time subtract this, then we'll see that the difference satisfies a homogeneous system. This means that indeed any Y can be obtained from X by adding a solution to the homogeneous system, which in this case is Y minus X. So Y minus X is a solution. Also, this means that that a solution to a non-homogeneous system can be, so solution set can be of three different types. It can be empty, so sometimes a non-homogeneous solution system has no solutions. It can be a single point, or if not, automatically there are infinitely many. Why? Because if you have just two different solutions, you subtract them and you obtain a solution to the homogeneous system. And because you have a non-trivial vector in the solution set for a non-homogeneous system, and you know that this solution set is a linear space, you can multiply this homogeneous solution by any constant. It means that you have, if you have one non-trivial X here, you have infinitely many non-trivial X's here, which you can add to a fixed particular solution, and therefore the solution set is infinite now. And actually, this is very convenient to understand geometrically. I often tell my bachelor students that the definition of linear algebra is that it's not algebra, it's geometry, and a little bit of analysis. So why geometry? Because we saw that actually any linear transformation is just about transforming spaces. And how can we understand the structure of the solution set? Look, this solution set is, okay, now on the right edge on the page here. Here, oh yes, here, thank you. Plus. Okay, thank you. So, if you have a vector so this is X, vector X, and it just a point in Rn, and the solution set to so all X's such that AX is equal to B, the solution set, can be described in the following way. So this is a hyperplane which passes through that particular point. This is sorry, it's not necessarily hyperplane. It's just some linear subspace of Rn which passes through these points. So it's not linear space any longer. It's what we call affine. Affine means that we just shift our linear subspace by some vector, and this vector is precisely any particular solution, because if you take now anything here, any vector from the origin to any point here, then this difference, this blue vector, will be in, so if this is x, this is y, and then this will be y minus x. So this vector y minus x is in this solution set for a homogeneous system. And vice versa. If you are already on this affine subspace and you take any 2 points, then the difference is in this. So, or you add this any blue vector to any point x there, then you'll still be in this affine subspace, and therefore you'll have solution to a homogeneous, non-homogeneous system. Okay, so we mentioned that non-homogeneous system may have 0, 1, or infinitely many solutions. How many solutions can a homogeneous system have? At least one. It always is consistent. Why? Yes, trivial solution is always 0, so is always a solution. So the first case is never realized for a homogeneous system, but it still is important to know how many solutions do we have in a particular situation. So how do we tell that a particular system has no solutions, or has just one solution, or has infinitely many? We can understand this by looking at the row echelon form. What is row echelon form? Well, in general, if you want to solve the system, you remember probably this from your school math, school algebra. If you have a system of linear equations, one of the approaches is the so-called Gauss elimination, which means that we try to simplify the system, express one of the variables from one equation, substitute in the other. These operations mean that we just replace one system by a simpler version of it, which is equivalent to the original. What does it mean, equivalent? It means that this transformation doesn't change the solution set. Okay, so 2 systems are equivalent if they have the same solution set. And then the process of solving it means that we just try to replace the original system by equivalent, which is simpler, easier to solve. And by performing consecutive steps, we can reduce it to the most simple form. This most simple form is the so-called row echelon form. Do you remember what it is? It's just this staircase form where you have zeros below, and it's inconvenient because you can easily solve it. You see how to solve it. It's backward substitution or a Gauss-Jordan elimination substitution. So if we already have reduced our system to the row echelon form, then we can immediately read off from this form property of the solution set. Well, for instance, we see from the row echelon form when the non-homogeneous system is consistent. Well, row echelon form is special form in which we have some so-called pivot entries, which are the leading non-zero entries in each row. But sometimes we don't have non-zero. Some rows may have no non-zero entries in this row echelon form. And then if we perform these the corresponding operations not only on the coefficient matrix A, but on the so-called augmented matrix, which also involves this right-hand side B1, Bm. Correct? Should I write M or N here? M, because it's number of rows. So certainly these are not original ones, because after these manipulations we changed not only the coefficient matrix but this right-hand side as well. But still, if we find out the situation in which there is a row of zeros in A followed by non-zero entry here, we understand that such a system is inconsistent. There is no chance to find axes which would satisfy this. Okay, so the system is consistent if and only if the row echelon form does not have a row of this form. When we have all zeros in the matrix itself and non-zero entry in the row in the free right-hand side B. Okay, so in particular, if we want this system AX equal to be solvable for any right-hand side, very often we want to have an algorithm which would solve. So we have to solve a system, many linear systems with the same A but different right-hand sides. So how to make sure we can always solve such a system? Well, the only chance is that there is no such a row at all. Because whenever we have a row of zeros in row echelon form, then of course we can find out proper B, which after these transformations will have non-zero entry here. And that's it. Therefore, if a system is consistent for a system to be consistent for every B, the echelon form has to have no zero rows. And in other words, there should be pivot position, pivot entry in every row. Which of course has some imposes some restrictions on this matrix A. As a final remark, every system of the form AX is B is consistent for at least some B. Well, you just take any X, calculate AX, and take this as B. Now, what about uniqueness? Well, uniqueness of solutions for a homogeneous system can be easily answered in terms of free variables. Do you remember what free variables are? As if we reduce the matrix, coefficient matrix to a row echelon form, then there are columns with pivot entries, and there are without. So the columns without pivot entries are called free, and the corresponding variables are called free, just because if you try to solve it, you see that you can take any number any number for this free variable, any number for that free and that, and you can solve the system. So in order to have no freedom, so in order for a solution to be unique, we have to have no free variables. Otherwise, every free variables gives you an extra degree of freedom in the solution set. If we take a non-homogeneous system, then a unique solution means that there must be at least one solution, and this solution must be unique. So existence of solution means that there is no rows of this form in the row echelon form. We already discussed that. So that's existence. And uniqueness, again, as for, do you remember? Solution set for non-homogeneous system is an affine set. So you take any particular solution and then add any solution to a homogeneous one. So for uniqueness, you have to have just one solution for a homogeneous part, homogeneous equation, and therefore you combine this condition, existence, with that one. Well, if you want a system AX is equal to B to have a unique solution for every B, every right-hand side, then certainly, again, we combine the previous requirement on existence in this case, so there should be no zero rows in an echelon form of A, because otherwise we can always find the right-hand side B, which produces non-zero entry here, and there is no solutions at all. So this is necessary for existence. And again, uniqueness means that there must be no free variables. Anything special for matrices? Oops. Okay. For matrices of this form, that satisfy this requirement, such a matrix necessarily must be square. Okay, look, no zero rows means that there is pivot entry in every row. But there is no free variables, therefore there is also pivot entry in each column. So the number of pivots is the number of rows and number of columns. So the only chance to have what is called non-singular matrix is that it is square. Good. So this is a definition. Matrix A is non-singular if the system AX is B has a unique solution for every right-hand side B. Why having non-singular matrix is important? Yes, for this particular reason. If you have a non-singular matrix, you don't care about the right-hand side. We know that there is always a solution, and moreover, this solution is unique. So it's the best situation we can dream of, which is never realized in the real world, because real world matrices are typically non-square. Okay, but still, as a first attempt, we'll understand what's going on with the square matrices, and then develop our knowledge extend our knowledge for a more general system. Okay, so here is the statement which we actually already justified. The matrix an n by m matrix A is non-singular if and only if it is square. And these two conditions hold. Do you remember what we had there? Okay. So here are two conditions for existence of unique solution. But if we already know that the matrix X square, then it's not necessary to require both, because each of them just tells us that there is a pivot entry in each row or each column. So if you know the matrix is square, it's enough to require that the number of so it doesn't work this way. That the number of the number of pivot columns is equal to n or m, so there is maximum possible number of pivot columns, so no free variables, or the same that there is no zero rows in row echelon form, and because both of any of these statements give us precisely what we need, that there is pivot entry in every row and in every column. Pivot entry in every row means that there is no zero rows in row echelon form, and there no free variables means uniqueness. Good. Well, here is an example. If you have this 3x3 matrix and want to know when it is non-singular, then we immediately recognize that C must be non-zero, because otherwise we already have a zero row, and it will survive in the row echelon form, certainly. And then if we have this C non-zero, we can divide by C. This is one of the elementary row operations. And therefore we get 1, and with this 1 we can kill these 3 by using this Gauss elimination. And then we see that B is the only non-zero entry in the second row. Therefore, if B is 0, we again have row of 0. So B should be non-zero. We divide, therefore, if B is not, we divide by B, we get these 2 1s, and therefore we can we see that this. Okay, so I did something else here, but anyway, we swapped these two. We can swap, for instance, these two rows, or subtract, eliminate 2 and subtract it from the first. Subtract from these, that, and that, and there. Anyway, we'll get this A here, and therefore, again, the only chance to have this non-singular is that A must be non-zero. So A, B, and C non-zero is necessary and sufficient for this matrix to be non-singular. Now we have a very important notion of rank, and usually rank is defined as a number of non-zero rows in the row echelon form, but I call this a baby version of the definition. In a few moments, you'll grown up and we'll have a real definition of the rank. So a rank of a matrix is a very important indicator for many things. For instance, if rank of matrix is M, if rank A is M, what does it tell us if rank of a matrix is M?
M independent columns.
Yes, it is M independent columns, and because this is the maximum possible rank, because the rank cannot be larger than M. Look, it's number of non-zero rows. So it means that there is no non-zero rows. Therefore, there is pivot entry in each row, and therefore this system is, the corresponding system is always consistent. So rank M means that there is a solution of AX is B of AX is B, solvable for any B. What if rank A is N? What does this tell us? So once again, rank is number of non-zero rows. Therefore, this is number of pivot entries. If this number is equal to n, and n is the number of columns, this means that there is no column without pivot. So there is no free variable. And therefore, system has always a unique solution. Correct? Yes, it's not correct. Sometimes I will say some nonsense just to make sure you follow me. Sometimes I say nonsense just because I'm not clever enough, but then your task is to get me up. Good. So this is a very important characteristic of a matrix, and here are some properties of the rank. So by definition, rank of A is not greater than smaller of two numbers m and n, because it's a number of pivot, and there is at most one pivot in each row and one pivot in each column. If we consider the augmented matrix, we usually denote it A hat, then this augmented matrix has one more column. Therefore, there is a chance that in the row echelon form, one extra pivot will appear in that last column. But in any case, the number of pivots cannot decrease. So that's why by adding something to a matrix, we can only increase its rank. Existence of solution in terms of ranks can be expressed in this form, that rank of A coincides with the rank of its augmented matrix. Do you see that? Is it obvious? Why is it obvious? Because if rank of A is larger than rank of augmented matrix, this means that this entry here is non-zero. That's the only way to add, to increase the rank. You have zero row in A, which is not zero row in A hat. That's precisely what is written here. You have zero row in A and non-zero entry in the augmented matrix. So there is no solution then. And vice versa, if this situation doesn't occur, it means that whenever you have zero rows or zero row here, it doesn't create any problem, because in the corresponding place for the right-hand side, you also have zero. So you have no equation at all. You have complete zeros. You just can ignore this. Okay? Good. Then consistency. Okay, if AX is consistent for every B, then this means that A must be of rank n. Again, just because then there cannot be zero row at all. At most one solution for every B means that there is no free variables. And as we already discussed, this means that the rank of A must be n. Rank of A must be equal to the number of columns. Then we have at most one solution. There might be no solutions at all, but at least at most one. And non-singular means that the rank of A is equal to, by combining these two, the rank of A must be m to guarantee consistency. and rank must be equal to n to guarantee uniqueness. By combining these two, we see that the only way to get a non-singular matrix is to have it of full rank. Square matrix of full rank is consistent, if and only if. Good. Now, you certainly know how to multiply matrices. If we have a matrix A of size m by n and a vector x, column vector x of compatible size, and compatible means of size n, do you remember? M by n matrix operates on Rm and sends it into Rm. So A applied to X, or in other words, if we denote the rows of A by R1 and so on, Rm, then this multiplication means just that we multiply each row by X. So we calculate dot product of every row and that vector X. Okay? So that's what is written here. Or if we write it down entry-wise, so in full detail, then it is just A11 times X1, A12 times X2, and so on, A1n times Xn. That's standard definition. However, that's not correct way to multiply matrix by a vector. I mean, it is correct, but it's not the most enlightening, most convenient one. Look, I have here some entries in red, some entries in blue, and that's for purpose because a more interesting, a more convenient way of regarding the product of A and X is to write this product in a different, slightly different form. Look, special thing in this representation is that there is a repeated x1, and this x1 is combined with entries of the first column, A1, 1, A2, 1, and so on, AM1. By regrouping, by writing this as the sum of first vector plus second and plus the last, and then taking out this x1 from here and xn from there as a vector, we just are led to this representation of a product. Why is it more interesting and more convenient? How can we interpret this?
That would be some combination of X's.
This is written here. So AX is just a linear combination of the columns. Look, AX, A applied to X is a vector of these entries, X1, X2, Xn. So A times X is first entry of X multiplied by the first column, plus second entry X2 multiplied by the second column, and so on, last entry Xn multiplied by the nth column. So AX is just a linear combination of columns. So look, when is AX equal B solvable? Yes, if B can be written this way. In other words, if and only if B is a linear combination of columns, or as was suggested, linear combination, the set of all linear combinations of columns is called the column space of a matrix. So if and only if B is in the column space. And this is geometric interpretation of both AX and this solution set AX is B. So the set of AX's is subspace, linear subspace, which is called the column space just for this reason. And we only have a solution of AX is B if B is in that subspace. Well, we can extend this way of regarding the product of matrices not only to AX but to product of two matrices A and B. Just by regarding a matrix B as a set of K columns, we can represent the product of A and B as A applied to this stack of columns, and therefore by linearity we just perform this operation on every column separately. So we have AB1 in the first column, AB2 in the second, and so on. ABK is the last column. This is M by K matrix in the result. And again, the conclusion is that every column in the product is just a linear combination of columns of A. So every column here is in the column space of A. Therefore, by multiplying A and B, we do not increase the column space. We may reduce it, but do not increase. This will have very, very nice corollaries for an adult version of definition of a rank. Good. Well, of course, we can write it down in explicit terms. So each entry in here can be written down in full form, and then we'll see that the AJ entry of the product is just the following sum, which can be geometrically again interpreted as the scalar product of ith row of a matrix A and jth column of a matrix B. So this expression here is precisely what it gives us. So ith row of A times jth column of B gives you ij entry of the product. It's convenient. I don't know if you learned these tricks in your so if you need to multiply matrix A by matrix B, it's convenient to say 4 by 5 matrix and 5 by 3 matrix. How do we multiply them? We can just write down A and B this way. And then each entry in the product, ij entry, is just the scalar product of these ith row here and jth column there. So if you multiply this row by column, you'll get the corresponding ij entry. In this case, we have 4 by 3 matrix. 3 is the number of columns, and 4 is the number. 4 is the number of rows, and that's the way we multiply matrices. This is maybe nice to do it manually, but again, better understanding of the product of a matrices is by doing this matrix column interpretation, interpreted as we suggested before. Good. So maybe I'll just add a few words about multiplying vector by a matrix. So we can multiply vector by a matrix only if our vector is the row vector. Yes. Because to be compatible, you remember, to be able to multiply matrices, they have to be of compatible sizes. So if the first is m by n, the second must have n rows and any number of columns. So if this is fixed, then we know that the second entry in the first factor must be n. Therefore, if you want it to be one-dimensional, I mean, of size 1, this m must be 1. So the only way to multiply vector by a matrix is to take it a row vector. And then again, we can do it in the following way, interpret it as the following way. If you multiply row by a matrix, B is a set of columns. So we multiply this row by each column separately. So here is the dot product of a row and the corresponding column, C1, C2, and so on. Similarly, as we did with these column tricks in previous setting, we can rearrange the entries here and interpret this product as a linear combination of rows. So look, vector times the matrix B is just certain linear combination of rows of B. And the coefficients in these linear combinations are precisely the entries of A. So A times B is just a linear combination A1 times the first row plus A2 times the second row and so on. And this is just the situation which we can obtain from the previous by transposing. By taking transpose of AX, we get X transpose times A transpose, which gives us this situation. So this again leads to say statement that rows of the product AB are actually linear combinations of rows of B. So AB inherits columns from A and rows from B. Okay, so this is nice observation. There is nice and many far-reaching conclusions of or corollaries of this point of view, but we'll discuss them after 20-minute break. So that's great. Okay, guys, so we will continue. I wanted to start with a question. Did you know that you are not permitted to ask questions during lectures? Because you don't need permission. So nobody can grant you permission for what you have rights for, okay? So whenever you don't understand anything, something, then just stop me or shout loudly and we'll discuss it in more detail. Okay, so here comes the real definition of a rank of a matrix. First, we introduce the notion of a column space. We already mentioned it. It's just the linear span of all columns. And we already know that this column space is precisely the set of all vectors of the form AX. That's very interesting, very important observation, which we'll use very intensively tomorrow when we'll discuss least square solutions to a system. Okay, in similar way, we introduce the notion of a row space, which is just the linear combination of rows of a matrix. And then rank of a matrix is just the dimension of its column space. And it turns out that that's the same as the dimension of the row space. And we'll prove it in a second. It's very important and non-trivial property statement that dimensions of the row space and the column space are the same. But we'll give a very, very short proof, or rather idea of the proof, in a few seconds. Actually, everything is here already. For instance, what we get is that the left multiplication of A by a non-singular matrix doesn't change the rank of A. So if we have A and we multiply it by a non-singular matrix B from the right, from the left, A, and we multiply it by a non-singular matrix B. What can we say about the ranks of BA and rank of A? Can we compare these two numbers? Is there any relation? Less or equal? Why?
Because multiplied matrices has its columns, combinations of columns of A.
Yes, precisely. We already know this. Look, every column of BA is a linear combination of columns of A. Do you remember? It's the other way around. Sorry. Okay, so now we do this way. So columns of AB are linear combination of columns of A. Therefore, each column of AB is in the column space of A. Therefore, this subspace is in the column space of A. Therefore, the dimensions obey this inequality. Why equality if B is non-singular? Any idea? Well, it does. You can take zero matrix B, for instance, and then everything goes to zero, and therefore there is a strict inequality here. Why non-singular doesn't change the rank?
We just rotated the space and we still can solve the elements of column space.
Those it doesn't transform into the lower dimension.
Why not?
Because it has the number of rank of its dimension, and when you
Say it once again.
Because it's a maximum for.
No. Well, A can be of rank 1, so we don't have to take A of maximum rank. Any A, for any A, if B is non-singular, then in fact there is the equality here. Again, it's all here already. Look, what I do, I represent, so we need, other words, the reverse inequality, that rank of A is less or equal than the rank of AB. And look, what I do. Oops. Does it explain? Look, what is here is a matrix AB multiplied by non-singular matrix B inverse. And here we have matrix AB. So that's precisely the situation we had here. But just now, this A has become AB, and this B has become another non-singular matrix. But who cares? Okay. So it means that actually that's the algebraic explanation, but what you wanted to suggest was a rather geometric explanation that non-singular matrix does not change the dimension. So non-singular matrix B means that B sends Rn into Rn in a one-to-one way. So it's a bijection. Non-singular means that all Rn is mapped into all Rn, one-to-one. Why? Because non-singular means that, you remember the definition? What is non-singular? No, that's not definition.
No, I mean explanation. Maybe because when we don't squish this space.
Yes, but why? Why? One solution for every right-hand side. So look, By is equal to C has a unique solution for every C from here. It means that if we consider this B as a mapping from Rn into Rn, what is possible right-hand sides? Anything, because for any C here, we can find Y, which is mapped into that. And it is also one-to-one, because different Y's are mapped into different C's by uniqueness. So existence gives us that the image is the whole Rn, and uniqueness means that this is one-to-one, therefore we can invert it. So this B inverse then B inverse applied to C is equal to Y. Now, what is the column space of AB? Column space of AB is the set of vectors of the form ABX. Correct? But look, you know that we can multiply, there is associative law. It means that if you have three matrices A, B, and C, and we have to multiply A by B by C, we can do this in two ways. First multiply A and B and then C, or first B, C, and then A. So what I suggest to do is to first multiply B by X. If X is anything here, BX will be anything there. Everything. Okay? So in fact, the set of vectors BX is just this, the whole Rn. If we denote it by C, like here, we can write that this is the same as AC, the set of vectors of AC, where C is any vector in Rn. But that's the column space of A. So this is geometric interpretation. Non-singular matrices perform a one-to-one transformation of Rn into Rn. Or as you suggested, this is just, it might be considered as a change of basis in Rn. We'll discuss it later. Okay, so these arguments give us very clear understanding what's going on with rank under such transformations. For the same reason, we have inequality here, because look, if we don't know that B is 1-to-1, B is any transformation, then we don't know that the set of vectors Bx gives us the whole Rn. It's probably some subspace, and therefore what we have here is only part of the column space of A. So again, the same reasoning, more geometric, I would say, give us explanation of these facts. Now, okay, left multiplication by a non-singular matrix doesn't change rank of A as well. We can explain why it is so by taking transpose. Do you know that AB transpose is A transpose B transpose? Yes? So I made long enough pause to give you a possibility to shout, it's nonsense. But you haven't. Okay, so this is not, it's not true. What's wrong? Order is reversed. We cannot multiply A transpose by B transpose because the sizes do not match. Okay, but the actual true equality is product of transposes in the reverse order. So everything we know about columns of AB also holds for rows of B transpose times A transpose. So in other words, if you want to interchange the row of the order of multiplication and derive some property of BA rather than AB, we just take transposes and work with transposes. Anyway, so it shows that non-singular matrix doesn't change the rank, no matter if you multiply it from the left or from the right. Okay, but now look. Look, what is row echelon form? How do we get row echelon form? How? Gaussian elimination, yes. Or actually there is this three possible elementary row transformations. Do you remember? Multiply any row by a constant, or swap the rows, or replace one row by sum of this row and multiple of another row. Three elementary operations. And actually these three elementary operations are just left multiplication by the corresponding matrices. Do you remember how we multiply B by A? What is going on with the rows? Rows of BA are linear combinations of rows of A. So by taking the corresponding matrix B, we can replace, say, row number 1 by row number 1 plus row number 2. Yes. Anyway, elementary row transformation is just the left multiplication by some matrix, non-singular matrix. Important thing is that each of these elementary matrix is invertible. Just because these elementary row transformation are reversible. We can go back, always can go back. If we have multiplied something by a constant, we can divide it and go back. If we swap the rows, we can swap them again and go back. If we replace first row by first plus second, we can subtract this second row and go back. Okay, so that's why this matrix B, which we use, is non-singular. It's invertible, and that's why row echelon form is actually the result of combining all this left multiplication and A. So if I combine all transformations into this B, then we see that this row echelon form R is just B times A. You already know that rank of BA is the same as rank of A. Yes? No. Why? Yes, and why? Why doesn't it change? Because it proved it 2 minutes ago.
Yes.
Is it a good argument? Okay. So now look, rank of A is the same of rank of BA, but look at this nice BA, it's row echelon form. So what is the column space of this row echelon form? Well, it's difficult to say, but we know that this column space is actually spanned by pivot columns only. Do you see that? Well, do you see that whatever is here, it can be obtained from that column? Whatever is here, it can be obtained as a linear combination of these two pivot columns, and so on. So the fact is that column space of this row echelon form is spanned by pivot columns. Therefore, the rank of this row echelon form is equal to the number of pivot columns because they are independent. Do you see that rows, pivot columns are linearly independent? Look, you cannot take any linear combination, not trivial linear combination of these three columns to have 0. Why? Because the only way to get 0 here is to take this column with coefficient 0. Otherwise, this entry, which is not present in the previous, will not get cancelled. Therefore, you must have 0 here, you must have 0 there, and now you must have 0. So there is no non-trivial linear combination of these pivot columns, which gives 0. So they form bases. Therefore, the dimension of the column space of R, row echelon form, is equal to what? Number of pivot entries. I don't know why pilot is pilot and pivot is pivot. Oh, but it's pivot. So rank of BA is equal to the number of pivot entries. But also, if you look at the row space of this R, the row space is also spanned by these non-zero rows. Therefore, the dimension of the row space is also equal to the number of pivot entries. And that's why we proved the theorem that the rank of matrix is the same as the baby version of the definition, which is the number of pivot entries or pivot rows, non-zero rows, in the row echelon form, or it's the same as the dimension of a column space of A, because we know that it is the same as the dimension of the column space of BA, which is our R, or the same as the dimension of the row space, because again, the dimension of the row space of BA is the same as the dimension of the row space of A, and it is equal to the number of these pivot entries. So that's the description or property of the rank. Well, corollary which we already know. We know this inequality, we proved it. Rank of AB is never greater than the rank of A just because columns of AB are in the column space of A. So we cannot increase this subspace. And taking transposes, so swapping rows, changing rows to columns, we can also, oh, sorry. Okay, so this is the B. Yeah, so interchanging this, we can prove also this inequality, that rank of AB is never greater than rank of B of the second vector. Good. And now we already discussed dimensions and bases, and just a very quick reminder of what it is. What is the main object of linear algebra? Transformations of vector spaces. What is vector space? Special fact. What is vector? Some point. Array. Well, there is an abstract definition of the vector space. Vector space is a collection of elements together with the two operations. These being multiplication by a scalar or addition. For instance, set of functions on 0, 1 is a vector space. Why? Because you know how to multiply a function by a constant. You just multiply its value. And you know how to add functions. F plus g at the point x is just f of x plus g of x. Okay? So this is abstract definition of a vector space, and very often it's very useful to just get rid of these particulars which we have in mind when we consider a model linear vector space which is Rn. Again, in a few minutes we'll see that any finite dimensional vector space is basically Rn, so we don't need anything except Rn. But there are not all vector spaces are finite dimensional. There are infinite dimensional vector spaces, and sometimes it's important. For instance, Fourier transform, you know, Fourier transform. It's the way to treat functions of on intervals, which give us the an example of infinite dimensional vector space. Okay, good. So now, if you have this abstract or just particular, if you are not comfortable with abstract linear vector space, just whenever you see V, imagine this is Rn. Okay, so Rn. Subset S of this vector space is called linearly independent if there is no non-trivial linear combination of any vectors in this subspace producing 0. For instance, we already discussed that pivot columns in row echelon form give us linearly independent set. And we explain why it is so, because if you just try to make everything 0 in the linear combination, you have to make 0 here, there, and this coefficient here must be 0, then here, there, 0, then here, 0. So there is no chance to get it non-zero if at least one of the coefficients in the linear combination is non-zero. Yeah, alternative property is the set S is linearly independent if and only if none of the vectors can be in this S can be represented as a linear combination of the other vectors. And here are examples of linearly independent sets in some vector spaces. Look, if you have Rn, then the standard basis vectors 1, 0, 0, 0, then 0, 1, 0, 0, 0, 1, give us linear basis, so linearly independent set. If you consider functions, more exactly polynomials, then in this set of all polynomials, there is infinite set which is linearly independent. So set of functions, constant function 1, then x, x squared, and so on, is linearly independent. Therefore, there are infinitely many linearly independent vectors. If we consider collection of all m by n matrices, this is also a linear vector space. It's basically the same as R m times n, but it's convenient if you have matrix, it's convenient to keep this form. So when are columns of a matrix A, m by n matrix, linearly independent? It's written here, yes. You're now paying attention to what is written there, not only what I'm saying. So look, we have m by n matrix A. And want to know when the columns of A, so C1, C1, C2, and so on, the columns C1, C2, Cm of this matrix A, when they are linearly independent. Correct? Answer is never. Because this is not correct number, so it's Cm. Oops.
M is smaller than.
So these are columns of this matrix. What does it mean that they are linearly independent? Well, we want to find a linear combination. So I take constant x1 times c1 plus xn times c plus cn. This is a linear combination, any linear combination of these columns, and we want to make it 0. But that's probably 5th time today when we use this rule for multiplying A and X. Do you recognize it's just A applied to a vector X, where X is precisely X is a vector this vector. I was waiting for this transposed. Good. So now we see that columns are linearly independent if and only if there is no non-trivial solution to this equation. So the null space, that is the set of all solutions to the null space, this is the set of all solutions. What should I write here? Here. And okay. This is a null space. Solution set to the homogeneous equation Ax is 0. So columns are linearly independent if and only if this null space is trivial. Yes? Yes. So we have a very nice description of this linear independence of the columns in terms of the null space. If we have echelon form, yeah, if you already used that, if we have an echelon form, row echelon form of A, then rows with pivots and columns with pivots are linearly independent. If we consider matrices, the set of matrices, m by n matrices, then it is a linear space by itself, and there are lots of linearly independent subsets. For instance, we can consider these unit matrices, basic matrices, which are everywhere 0, but at one particular place for particular I and j, where we have 1. So these, we have n times m such matrices, and they form linearly independent set. Because whenever you take any linear combination of these, what you'll get is the matrix where these coefficients stand on the respective places. Yes, please.
Can you please tell more about non-trivial solutions except of only zeros? Are there any other non-trivial solutions?
Oh, well, look, whenever columns are linearly dependent, it means that there exists at least one non-trivial linear combination. So you have this x1, x2, xn, not all equal to 0, which satisfy this equality. But that means that if we consider the corresponding vector x here, then we see from this that A applied to x gives us a 0 vector. Therefore, such x is in the null space of A. So null space of A is then non-trivial. It always contains 0. But if columns are linearly dependent, it also contains non-zero vectors, and any solution to these produces such a vector. Any linear combination producing 0 generates the corresponding vector in the null space. So you take the coefficients in this linear combination and you get vector x1, x2, xn, which is in the null space. Trivial solution. Yeah, that was the question. What is? Oh, sorry. So trivial solution is 0 solution. It's trivial. Yeah, that's it. That's it. Sorry. So trivial means 0. It's trivial because it's always there and there is nothing special. Good. Now, here is an example of 3 polynomials which we can check for being linearly independent. Well, if we try to find any, consider any linear combination of these 3 polynomials and try to find a coefficient C1, C2, C3 such that we get 0. Well, we immediately see that this amounts to having all coefficients in front of 1, x or x squared being 0, which in turn means that we have just linear system, homogeneous linear system. And existence of non-trivial solution of this is equivalent to linear independence of the columns, for instance, as we have seen. So we reduced that question to the question of linear independence of the columns. And well, we can answer the question by just analyzing the row echelon, well, by solving this system and trying to find if there is any non-trivial solution. Good. Now, very important notion related to the linear vector space is that of a basis. So basis of a linear vector space is just any subset which is both linearly independent and spanning. Spanning means that every vector in V can be obtained as a linear combination of those from S. And the examples are, for instance, here, standard vectors E1, E2, and so on, En in Rn, so 1, 0, 0, 0, 1, 0, and so on, form a basis because we have seen they are linearly independent, but they are also spanning because if you have any vector xn, then it it is x1 times 1, 0, 0, 0 plus x2 times 0, 1, 0, and so on, plus xn times 0, 0, 0, 1. And this is precisely x1 times E1 plus xn times En. So you see that any vector in Rn is a linear combination of these E1, E2, En. Therefore, they are both, and again, this also shows linear independence, because if we have this equal to 0, this is only possible. This is only possible when all x's are 0. Okay, so this is both independence and spanning. Therefore, it's a basis. In a similar manner, we can show that functions 1x, x squared, and so on form a basis for Pn, the set of all polynomials of degree at most n. And these matrices Mij.
Why P? What does it mean, Pn?
P,
Yeah.
P is for polynomial. P, first letter of polynomial, n is the maximal degree of this polynomial. So Pn is a linear set of all polynomials of the form C0 plus C1x plus Cn times x to the power n, where you have any C1, C2, C0, C1, Cn. And here, this is n. Sorry. N. I just wrote it this way. Good. Matrices we discussed before, which have only one non-zero entry on place ij, form a basis in this set of all matrices of size m by n. This set is a linear space because we can add matrices, we can multiply matrix by a constant. So this is a linear vector space different from Rn, and here is the basis. This form basis for that subspace. Basis is not unique. Yes, please.
May I ask you, what about subspaces? If you have vectors that span a subspace, do these vectors span holes?
If they do, then they do. If they don't, then they don't.
You a little bit elaborate about subspace. What is
Subspace? Okay. What is subspace? It is a part of a vector space which is closed under these two operations, additions and multiplication by a constant. So if there is an ant which is crawling through this plane, then the world for it is two-dimensional because it only goes to the on this plane. But this plane is immersed in 3 dimensions. So we have 3-dimensional vector space R3, and this is its subspace R2, if this point is the origin. So this is subspace 2-dimensional, and for ant living on this plane, the world is 2-dimensional. It doesn't know of existence of any other vectors except that. So it's this is a linear vector space by itself, but it is part of something larger.
It's not correct to say that R2 is a subspace of R3.
Did I say it R2?
No.
I said plane. This is a plane in R3. It is not R2. But formally, it's not correct to say that R2 is a subspace of R3 unless you identify R2 with the XY plane in R3. Okay, so
Setting 0 to Z0.
yes. So you identify this R2 with the plane of the form X, Y, 0. Then you have this subspace in R3. But R2 is not a subspace of R3 just because they don't have any common vector. Give me a vector which is simultaneously in R2 and in R3.
0 vector?
No, a 0 vector in R2 is 0, 0, and 0 vector in R3 is 0, 0, 0. Do you feel the difference? Okay. 1, 0, but it makes great difference.
And does subspace always have a smaller dimension than its space, or we can have some dimension subspace and space?
We didn't we haven't introduced dimension yet. And you'll be able to answer your question in a second. Okay, so bases are not unique. Because here is an example of a basis in R3 which is different from the standard one, just because we can make sure these 3 vectors in R3 are linearly independent and spanning. How? We again consider all possible combinations and try to solve the corresponding equation for any right-hand side B. And therefore, if we make sure that these columns, that the solution always exists, so the set is spanning, it means that that these 3 columns are basically okay. Spanning spanning means spanning. But if we want to check that they are linearly independent, then we just make sure that the homogeneous system has no solution, and we check that non-homogeneous system always also has a solution. This can be easily done in this particular case because we see that this matrix is non-singular, and therefore indeed the corresponding solution, homogeneous solution, has only trivial solution, which means that the columns are linearly independent, and solution exists for every right-hand side B, which means that these 3 vectors are spanning. So they span the whole R3 because this has always a solution, and they are linearly independent because the solution is unique. In other words, because the homogeneous solution, homogeneous equation has only trivial solution. So bases are not unique, and we can introduce now the notion of the dimension of a vector space. We say vector space is finite dimensional if it possesses a finite basis, and otherwise this subspace is infinite dimensional. Do infinite dimensional spaces exist? An example? Yes, polynomials. We have seen that polynomials have infinite linearly independent set. And in fact, this set is also a basis of this vector space. And you already know from your homework that if you have a space of dimension n, the maximal number of linearly independent vectors there is also n. So you cannot have more. Well, but the important thing is that this definition, okay, that any two bases in finite dimensional space have the same number of elements. And this number, common for all possible bases, is called the dimension. This is actually proof of one of the home tasks, because it tells us that if we have two different bases, and assume we have two different bases, and assuming that one is larger than the other, that is has more entries, we derive a contradiction by showing that that these vectors v1, v2, vm cannot be linearly independent, because we find non-trivial linear combination. There are non-trivial linear combination which produce 0. Why so? Well, it's just again reduced. This question is reduced to the solutions question on the solution set of a system of this form: C times A is equal to 0. Here, the vector of unknowns is C, and because we assume that m is larger than n, it means that A has more rows than columns. And therefore, not all rows have pivots. And therefore, there are a linear combination of these rows which produce 0. Why? Once again, look. If we have this picture, we can say that these first, second, and the third row of a matrix A form a basis, and then what we can do, we can express any other row as a linear combination of these basis rows. Therefore, this equation has a non-trivial solution, because, as you remember, C times A is just a linear combination of rows now. Do you remember? So there is non-trivial linear combination of rows which gives us 0. That's why any two bases have the same number of elements, and this number is called the dimension. So Rn is of dimension n. This is of dimension m by n. Why? Number of matrices? No, there are infinitely many matrices. Yes, because we know basis, one particular basis for this space. This one particular basis consists of matrices of the form Eij, where we have all zeros, but on the in one place, one entry, only one entry is non-zero, and we can take it 1. So these matrices are linearly independent, because if you consider any linear combination of these matrices, say if you consider the matrix linear combination of the form Cij times Eij, what you'll get is just this matrix with entries Cij. To make it 0, you should take all C's equal to 0, but that's trivial linear combination. So that shows that this set is both spanning and linearly independent. Therefore, it's a basis. How many elements, how many vectors are there in this set? M by n. Are you confused that I call this vector? If you regard this set of matrices as a vector space, if you regard this is a vector space, then every element of this set is called vector. That's why by saying matrix is a vector, we mean that this matrix considered as an element of the vector space is just an element of this vector space. Okay? So let's see. The set of polynomials of degree n, at most n, has dimension n. Why plus 1? Yes, because we always have 1 x up to x to the power n, so it's n plus 1. And so on. Space of diagonal n by n matrices is of dimension n. Diagonal matrix is matrix whose only non-zero elements are on its diagonal, main diagonal. Okay. Is it trivial? It's clear. What is the basis? Yes, it's basically EII. You take only the only one on the corresponding place on the diagonal. Good. Upper triangular n by n matrices have dimension n times n plus 1 over 2, because upper triangular means that everything which is below the main diagonal is 0, and there are precisely so many entries that might be non-zero. Well, if you have consider 3 by 3 the set of 3 by 3 non-singular matrices, what is its dimension? Nine? So, okay, 3 by 3 non-singular matrices. What is its dimension? Non-singular. 3. Nine. There's more. For 9. Okay, let's vote. Who is for 9? Who is for 3? Sorry? Yeah, you're right. It's a nonsense. The set of non-singular matrices is not a linear subspace. Therefore, it has no dimension. Do you understand why non-singular matrices do not form subspace in 3 by 3? Well, yes, there is no linearity property here. I mean, first of all, every linear vector space contains a special element called 0. 0 is a neutral element under addition. It means that if you add any 0 to anything, it will not get changed. 0 matrix for matrices such as 0 is just matrix of all zeros. In Rn, such as 0 is vector of all zeros. So, but matrix with all zeros is singular. Therefore, this set has no zero element. Further, you can add two non-singular matrices and get singular one. An example? Yes, I and minus I. They are both non-singular. If you add them up, you will get zero. So this is not linear subset. Therefore, the notion of dimension is not defined at all. Okay, and for finite dimensional vector spaces, you know that any basis has dimension, cardinality n. So the number of vectors in the basis must equal the dimension. If you have any such set, then it's not necessary to check that this set is both linearly independent and spanning. In fact, any of these will imply the other. So any three vectors in R3 which are linearly independent form automatically a basis. Or if you have three vectors in R3 which span the whole R3, they also form a basis. So you don't have to check both properties in the definition if the number of elements matches the dimension. And if it doesn't match, there is nothing to change, to check, because there is no chance that this set is a basis. Okay? Once again, if you want to make sure that set of 10 vectors in R11 is a basis, you just say it is not, because any basis in R11 must contain 11 vectors. You have 10, so no chance. But if you have 11, then it's not necessary to check that they are both linearly independent and spanning. One of these properties, together with the correct number, will imply the second. So in this statement, any three, any statement implies the other. You have questions, Natalia?
If we have 10 vectors in 11 dimensions,
Yes.
Can they be linearly independent?
Can or can't they? How do you think? They can be, of course, they can be, because, well, even more is true. Whenever you have 10 linearly independent vectors in R11, you can add one extra vector which is not in the linear span of these 10. And these, combined with the previous 10, will form a basis. Why? Because these 11 new vectors will span everything.
Using span form subspace.
Say it once.
So then from 11 form subspace. So from this 11 dimension.
Look, any set of vectors form a subspace. This subspace is called linear span. Yes? You consider these two vectors in the plane, and you can form a subspace spanned by these vectors. But if this is R3, and you have this plane, you can take any other vector here or there. So you have four vectors in this plane, and they span subspace. This subspace is the same if you take just this two or that two or any. Okay. So any set of vectors form a subspace which is called linear span. It's just set of all possible linear combinations from these vectors. In particular, if you have 10 linearly independent vectors in R11, they form a 10-dimensional subspace of R11. Because they are linearly independent, number one, and they span their linear span, by definition. Okay, so these 10 vectors are both linearly independent and spanning for that subspace. What is wrong here? These 3 vectors in a 2-dimensional subspace, yes, they are not linearly independent. The span is the same, but they are not linearly independent. So that's why they don't form basis for their linear span. Okay, good. Well, so here is another explanation why any linearly independent vectors in Rn form its basis. Because we know that linear independence means that there is no non-trivial solution, for instance, for the, so it's okay. We already know they are linearly independent. Okay, so we have linearly independent vectors, and we need to show that there is solution to every right-hand side B. So there is a linear combination. We need to show that they are also spanning. So in other words, we need to show that this for every vector B, there is a non-trivial combinations of C1, constant C1, C2, Cn, such that the linear combination is equal to B. But we can regard this equation as again as matrix vector multiplication. If you consider these vectors as a columns of some matrix A, then this equation is just AX is equal to B. And because the columns are linearly independent of this matrix, the matrix is non-singular. Why? Why, if columns are linearly independent of a square, this is square matrix, n by n, why, if its columns are linearly independent, it is automatically non-singular? Yes, because we have n pivots. We don't have free variables. So we don't have 0 rows. So it means that it is non-singular. Therefore, we guarantee the existence of the solution AX is B for every right-hand side B. That's why it is spanning. So linearly independent set of n vectors in Rn is automatically spanning, and this is the proof of the previous theorem. So we proved it, basically. So we proved it, that spanning implies independence implies spanning. By in the same manner, we can prove that spanning implies independence. Good. Yes. Do you know what is TFEA? TFAE. Yes, the following are equivalent. This is standard abbreviation. Okay. Well, now look. If we have a basis of a vector space, then we know that it is a spanning set. Therefore, any x in this vector space can be written as a linear combination of basis vectors. Hello, are you still here? Okay, once again, we have a basis V1, V2, Vn of a vector space V. Take any x in this space. Then my claim is that every vector x can be written as a linear combination of these basis vectors. Why? By definition of a basis, basis is spanning set. Spanning means that linear combinations exhaust the whole V. Okay? So for every X, there is at least one linear combination of these basis vectors producing X. The claim is that such a linear combination is unique. And it's a very simple statement, because if we had two different and if we subtracted, then we could represent 0 as a non-trivial linear combination of these vectors, which would mean that they are not linearly independent. A contradiction, because basis is also linearly independent. Okay, therefore, what we now have is that if you fix a basis, then basically every X can be uniquely given by a linear combination, and therefore for every X there is a fixed set of coefficients C1, C2, Cn in this linear combination. For every X, we have unique C1, C2, Cn in this equality. As we have proved. Therefore, we can consider this as a mapping. So every X in, say, V generates a set of coordinates C1, Cn with respect to this basis, which is now a vector in Rn. We can consider these coefficients, combine them in the column vector, and consider it as an element of Rn. So for a fixed basis, yeah. These Cj's are called coordinates of X in this basis, and this vector C1, C2, Cn, considered as an element of Rn, is a coordinate vector. And then a very important thing is that this mapping from X to the coordinates can be considered it's called the coordinate map, because it associates coordinates with every vector X. It is denoted by Ts if S is this basis S. S is the basis. And the mapping from X into its coordinates is called coordinate map. Then it turns out that this coordinate map has the following properties. It's linear. It means that if we have a linear combination AX plus BY of two vectors X and Y, and want to calculate the coordinates of this combination in the basis S, we can just first find coordinates of X, coordinates of Y, and just combine them in the same linear combination. It means that this mapping TS is linear map. It is linear. In general, a linear mapping is called an isomorphism if it is linear one-to-one and onto. One-to-one means that no two vectors are mapped into the same vector. One-to-one. Onto means that in the image we have all the vector space there. Then it turns out that this coordinate map from V to Rn is an isomorphism between V and Rn. That means that actually there is only one n-dimensional linear vector space, and this linear vector space in R is Rn. Rn is a model space for every n-dimensional linear vector space, because after fixing a basis in this vector space, we can forget about the nature of the elements in V and only consider coordinates. Look, when we have polynomials C0 plus C1x plus C2x squared is much information encoded in this x and x squared. Not very. What we need to know are just these three numbers. So there is a one-to-one correspondence between this polynomial and the triplet C0, C1, C2. Moreover, if we want to add two polynomials, say we want to add this to polynomial D0 plus D1x plus D2x squared, what we do, we just add coefficients. So we just take here D0, D1, D2, and add these vectors. That's the same. So it makes a little sense to write down the polynomial in this full form. It's just enough to indicate its coefficients. And this is one-to-one correspondence between all polynomials of degree at most 2 and all vectors in R3. Take any vector in R3, say 1, 2, 3, and you know which polynomial corresponds to this. It's 1 plus 2x plus 3x squared. So this is the meaning of this statement, that actually if we fix a basis, then any n-dimensional linear vector space looks like Rn. Because every element of this vector space can be associated with the coordinate vector, and this is an element of Rn. And this is one-to-one, and it's a linear, which means that if you want to add polynomials, we actually are adding coefficients. So it doesn't matter if we write it in this complete form or just write down the coefficients. Here is why it is this coordinate map is one-to-one and onto and linear. Well, linear, we already said it's more or less clear, but why it is one-to-one? Look, if we have Ts equal to C, then it is just another way of writing this equality. That's the definition. Yes or no? It's definition. That's how we introduce this vector of C's. Vector of C's, coordinate vector, are just exactly the coordinates, coefficients in the linear combination. Now, if we take two different sets of C's, we cannot get the same x, because we know that every x has a unique representation in terms of basis vectors. That's why it is one-to-one. No two different coordinate vectors are mapped into the same. So not two different axes are mapped into the same coordinate vectors, because here is the representation. Here is explicit form for this x in terms of C. And it is onto because every vector x has at least one representation as a linear combination. So for every x, oh, sorry, no, it's vice versa. It's onto because given any set of coordinates, we demonstrate, we give x with these coordinates. It's precisely this formula which works both ways. You take any c's, and here is the x with these coordinates. Therefore, for that particular c, that x produces this coordinate vector. So this is just different ways of looking at this, but the main idea is that bases are important things because they allow us to forget about the structure of the vector space. It could have been matrices or functions or just anything. But after we have fixed the basis, everything looks like a standard linear vector space Rn. And that's basically what we wanted to say. There are a few more examples, and another one maybe important thing I would just pay attention to is that what is a matrix? We started with the statement that matrix X is actually, every matrix is actually a linear transformation. And it is indeed so. If we take any linear transformation between vector spaces, then it can be encoded as multiplication by a matrix. And this is the explanation. So if we have linear mapping between Rn and Rm, then this mapping can be realized as a matrix multiplication for a particular matrix A, which we can identify very easily. And this matrix A is matrix with columns v1, v2, vn, where vj is just the image of the jth standard basis in Rn. And the proof is just this statement. Look, we have linear mapping T. We calculate T of x, but x can be written in terms of the standard basis of Rn. Okay, so this is standard basis of Rn. It can be written just as a linear combination of x1, e1 plus and so on. Because T is linear, we can write this as a linear combination of the images. So it's the same as x1, constant x1 times T of e1 and so on. But look, this is a vector in Rm. Yes. This is also a vector in Rm. So we have a linear combination of vectors and vectors in Rm. Now we regard these vectors as the columns of a matrix A, and we again recognize this probably for 11th or 12th time that we use this matrix vector multiplication rule. Look, linear combination of these vectors is just matrix composed of these vectors times the corresponding coordinate vector. So this linear combination is just more detailed way to write A times X. So matrices are just coordinate way to represent linear transformations. And why we multiply matrices in the way we do is just because we combine linear transformation in the same way. So roughly speaking, if we have T1 from Rn m to Rk and T2 from Rk to Rn, and if we consider a composite mapping, combine, we first apply T1 and then T2. So T1 maps Rm into Rk, then T2 takes this vector in Rk and sends it into Rn, yes. Then this composition is another linear mapping from Rm into Rn. So this is the composition. And it turns out that this linear transformation, the matrix of this linear transformation is just the product of the matrices of linear transformations of T1 and T2. So if A is encoding of T1 and B is encoding of T2, then composition of T2 and T1, or T1 and T2, first take T1 and then T2, has matrix BA. And that's why we multiply matrices as we do, because matrices appear just as linear transformations, and we write linear, we combine linear transformations in that way. So this is explanation why BA is indeed a linear a matrix of linear transformation, which is composition of T1 and T2. Again, the proof is very, very short. You just calculate them on basis vectors and you see the result. So that's it for today, guys. I know it for some of you it was a little bit dull because you know everything, or maybe you don't know anything, but it is not so important. The main thing is that you understand that linear algebra is not just manipulation of matrices, and we'll see it's not just matrices and manipulation with them tomorrow. So see you tomorrow at 4 p.m.